Welcome along to topic 1 of computer programming, and in this presentation there's a little bit of discussion about different types of language, then some programming constructs, and then looking at computational thinking. So first of all, types of language. So we have different types of language. Low-level languages are languages that are close to the CPU. So they don't provide very much abstraction from a computer's instruction set. And it's quite important in computer programming to get words for things. And abstraction is a common term used in programming. And a good way to think about abstraction is, let's say you go and drive to work, or you get the bus to work, or you get the bus to meet a friend. You don't care how that bus works. And also, you don't necessarily know how to drive that bus. Alright? Because these are abstracted from you. You only care about the fact that the bus travels along the road. So that's a kind of a way to think about abstraction. It's about concealing detail. So low-level languages are often written in the language of the processor. So for example, if we have an Intel processor, low-level code can be written to speak directly to that processor. So these are sometimes called being close to the hardware. Okay? Right, so high-level languages. Right. High-level programming language is a language that's got more abstraction from the computer system. So for example, Python is a high-level language, C++, C#, Java, JavaScript, all the languages that we use on a day-to-day basis. It's very unlikely you're going to be writing things in machine code or assembly language. But these high-level languages are languages, and often in a high-level language you'll type in like an English word, or it's close to a spoken language, and those are said to be further away from the CPU. So that's why they're called high-level languages. Higher level away. If the low level is close, the higher level is further away. So, some common uses for languages. We have this top 20 list of the most common languages that we have. So if you think about in our global society, we have a top 10 languages. I think maybe the most spoken language is Mandarin Chinese, and then maybe Spanish next, and then English. And I think maybe as a second language, English is first, or something like that. And then you have other languages, French, Portuguese. I'm trying to think of other ones where loads of people speak them. Maybe Japanese, Hindi, probably loads of people speak Hindi. So in programming languages, the number one at the time of taking this screenshot was Java, followed by C, followed by Python. However, let me just follow this link. This is an up-to-date link here, and let's have a look at this. So at the moment, in February 2020, let's just zoom this in a wee bit, the Python is the most popular language, okay, followed by Java, followed by JavaScript, followed by C and C++, followed by C#, followed by PHP, followed by R. Okay, then we have these Objective-C, Swift. TypeScript's very similar to JavaScript. MATLAB, I suppose, kind of similar to R. PHP is mainly used in web development, and some other ones, Ruby, Go, Visual Basic, Rust. Yeah, so Python is the number one programming language at the moment, as we speak, although these things change, they kind of swap around at the top. Alright, so some programming constructs now. It's very important when you're learning about computer programming to try to get names for things, okay? And it's good if you can call things by their actual name. So when you're constructing a program, you should think of the program as a set of primitive instructions, and the instructions get put together to make a program. And these instructions are very simple, just simple tests, print statements, arithmetic operations, and when we combine lots of these little things, we can combine them together in a program. Now, there's another program called an interpreter, and that interpreter, what it does is it reads each line of the program and interprets it, okay? And all it does is it walks through, it starts at line 1 or line 0 and it runs each line. And occasionally it might stop because there might be some kind of a test, and that test might say, okay, I want you to go to a different instruction, and then it'll start from that instruction and just keep reading. And all it does is run through the program one step at a time. Now, the test can change where the program counter is, where it's running. It might move to someplace else in the code, but as soon as it does, the program counter will just keep running from that point. Okay, so I've got a little diagram, roughly what this might look like. So over here we have some input device, and then we have the CPU, and we have some arithmetic logic unit inside there, and the memory and an output device. So if I just jump over to the console here, so let's say we have a Python shell here, and if I were to do print, let's just do something more simple. We'll say my variable equals 5. Okay, so what I'm going to do is just run that, and now if I do, so what I've done is I've created an area in the memory, in the computer's memory, called my variable, and I'm storing inside that the number 5. Alright, so now if I say print, right, my variable, and run that, the computer will return the value that's stored in the memory. Okay, now if I were to say my variable plus my variable, okay, what the computer's going to do is it's going to go to the memory, look up my variable twice, and it's going to, it already knows these purple things here are primitive values. The computer already understands those, and it's going to put together the two values of mine. It's going to send that to the CPU, and the CPU will reply with the answer. Okay, so that's what's really happening in the background. Now, that's a kind of overview. Obviously this isn't a hardware class. I just wanted to discuss exactly what's happening in the background. So now let's look at some computational thinking. So it's important to get into the habit of trying to think computationally when you have a problem. Alright, so computational thinking. Let's just move forward. Right. So what we should be aware of is that a computer can only do two things. There's only two things a computer can do. The first one is perform a calculation, and the second one is store the result. Those are the only two things that a computer can do. A computer cannot do any other thing apart from perform a calculation and store the result. You might think, oh well, hang on, my computer's got Netflix on it. Yeah, all that is a lot of calculations being performed and results being stored in RAM. Okay, so you're watching something on Netflix, all it's doing is downloading that from somewhere and presenting it on the screen. Okay, performing calculations about where to put the pixels and storing the results in RAM and then probably deleting them. So the computer can do this very fast, and we have a lot of places to store these results of programs. Now, when we want to think computationally we need to try and break problems down into their constituent, the steps that make up that problem. Okay, so we have these things called algorithms. So an algorithm is an idea, it's a recipe, it's a series of steps to solve a problem. Now, there's some problems that are just too hard for computers to solve, but many things we can do using a computer. So for example, if we wanted to work out a certain amount of values, calculations, we can teach the computer how to do that, and then we don't need to do it ourselves anymore. So a couple of examples of things that are too hard for computers to do: predict every move in a chess game that you're about to have. It's not possible. Predicting the weather on a very local scale. Okay, it's just a little bit too difficult, too abstract for a computer. Now, a program is an interpretation of an algorithm. So an algorithm is like a recipe for how to do things, and a program is that recipe written out in a language that the computer can understand. Okay, so here's a simple algorithm about how to get to work. Alright, so let's say you're trying to figure out how to get to work. You can start off thinking, right, okay, do I live near where I'm trying to go? If I do, let's walk there. Now, let's say it's far away. Do I have a car? Yes. Okay. Drive. Although if you're in Edinburgh, you'll know that's a very silly thing to try and do. Absolute nightmare to try and drive anywhere. And then, if that's not possible, you could try and get on the tram or on the bus somewhere, and that would get you there. Probably faster than you can drive, because there's various things, bus lanes and all that kind of stuff. So, these things have names, alright? This thing up here, where it says begin, is actually called a terminator. Okay, this oval shape. The diamond shape, okay, where is a decision, right? So there's always a yes and a no comes out of that. And the rectangle shape is a process. Okay, so for example, walking to work is a process, but do you work in walking distance from home is a decision, so it's a yes or a no. And the beginning and end are oval shapes. Those are just called terminators. Usually start end starts with these little program terminators when we make a flowchart. So how do we actually solve a problem? Well, the first stage, and actually the most important stage, is we need to understand what the problem actually is. We can't solve a problem if we don't know what the problem is. And so often the longest step is figuring out what it is you're trying to solve. Okay, so for example, in networking, if you have a part of the network that can't connect, or customers on the Wi-Fi and they can't get internet, you are not trying to get them internet. Well, you are in a bigger sense, but really what you're trying to do is trying to solve the network issue. And you can't solve that network issue until you know what that network issue actually is. So for example, it could be something as simple as a DNS issue, or it could be that a cable's unplugged. It could be that you've misconfigured the firewall. Okay, so you can't really solve it until you know what it is. And often, if you're working with networks, you'll become quite good at figuring out what the problem is straight away. But sometimes it's difficult to find out. So once you know what a problem is, you can break it down into steps, and then you can figure out some kind of way to solve each step, and then you can make an algorithm, and once you have an algorithm, you can write a program to solve that problem. So those are some kind of key steps. Now, when we're looking at each step inside a problem, there are different types of knowledge. Okay, so there are different things that we need to know. And when you think about this, you can break everything down into these two different types of knowledge. Okay? The first type of knowledge is called declarative knowledge. And declarative knowledge is facts. Anything that's a fact is declarative knowledge. Okay? The second type of knowledge is called imperative knowledge. And imperative knowledge is knowledge of how-to methods. So let's say I told you to go and do something very straightforward. Go and make a salad, or go and make some meal. Right. I'm assuming, or I hope at least, that you have the imperative knowledge to know how to do that. Okay, maybe you don't. Maybe it'll be it'll be a disaster. It'll be a microwaved lasagna or something like that. But maybe, you have the imperative knowledge to actually go, how to, like, chop up an onion, chop up some carrots, chop up some celery. Maybe you know how to do these things. So those are the imperative knowledge. The declarative knowledge are, do you know what a kitchen is? Do you know what a knife is? Do you know, what an onion is? Do you know what these things are? Okay, so those are the two. Now I've put a little to help you remember the difference between the two. I think, well, I don't know if this is helpful at all, to be honest, but there's a thing in Spanish and Latin called imperativo, and it's for giving commands. Okay, so like the Roman army would give commands that would be in the imperative. All right, so that's how to do something. If someone's shouting at you in the imperative, the declarative just means to make something clear. All right, so to declare something as a fact. So those are the two different types of knowledge we have. Right, so let's look at an example of some imperative knowledge. This one is attributed to Heron of Alexandria, who was around in the 1st century AD. And this is sometimes called the Babylonian method, and this is a way to figure out a square root of a number. Okay, so what you do is you start with a guess called G, and if G times G gives you the answer, you just stop and you say that's it, that's the square root. So let's say I'm trying to work out the square root of 4. X is 4. I'm going to guess that it's 2. I'll do 2 times 2, and does that get me close enough to 4? Yes, it does. Perfect. Stop. However, what happens when we're wrong? This is an imperative way, an algorithm of figuring that out. We take the average of G and X divided by G, and we get a new G, a new guess, and then we multiply that by itself, and if that gets us the answer, we stop. And I'm going to show you an example of that in a second. Now, there is one problem with this, and the problem is that this doesn't tell you how to find G. It tells you what to do with G, but it doesn't tell you how to find G. How do you tell the computer how to find the guess? Okay, and that's where we need some kind of declarative knowledge. We need some way of determining the guess. Okay, we can't just say to the computer, take a guess. The computer will say, well, what do you mean take a guess? I can take many guesses, but you'll have to tell me what those guesses are. Whereas if you say to a person, take a guess, a person will be able to do that no problem. So for example, if I said to you, I want you to guess a number between 1 and 10, you're probably going to guess 5. Because that's the middle. However, the computer can't do that. We need to teach the computer how to do that. We need to say, how guess? Do you want to go halfway between? Do you want me to guess 1 and 2? So we need some kind of declarative knowledge. So here is this algorithm of the square root. What I'm going to do is I'm going to show you this in action here. Now forgive me if I stumble a little bit on this one. So I'm going to open up a notepad here. Let's just make this a little bit smaller. Cover over, there's a picture of Heron there he is, happy. Make this a wee bit smaller here. and we'll grab a calculator as well, because I'm not going to try and do this in my head. So let's say, let's move this up a wee bit, and we can get the calculator over here. So let's say we're trying to figure out the square root, okay, of 36. Right, so what is the square root of 36? Now, I know for a fact that the square root of 36 is 6. I already know that. You know that as well. 6 times 6 is 36. If you didn't know that, then you do now, because I just told you. So we already know that, but what we're going to do is deliberately guess it wrong, so that we can then test out this algorithm, Heron's algorithm of the square root, to see if we can figure it out. Okay, so let's say the guess G is going to be equal to 4. Right, we're going to guess that 4 is the square root of 36. So let's first of all do 4 times 4, and that's going to give us 16. Right, is 16 36? No. Okay, we'll just put x equals 36 up here to make this clear. So we're going to need to use this formula over here. Now the first thing to do in the formula is work out these brackets, x divided by g. So let's do that first of all. Okay, so x is 36, and we're going to divide that by g. So 36 divided by 4 is going to give us 9, and then we need to say add g, so plus 4 is going to give us 13, and then the average of that. So there's two values, we're going to average it, just going to divide it by 2. 13 divided by 2 gives us 6.5. So that's the new guess, right? So G is now 6.5. Right, so is 6.5 times 6.5 36? Let's just work that out. 6.5 times 6.5. No, it's 42 points, so it's too high. So let's return to the algorithm, and we're going to take x divided by g. So x is 36. Divide that by 6.5 is going to give us 5.53, something long like that. So then what we're going to do is we're going to add that to g. So g plus x divided by g. So let's add 6.5 to give us this number. And then we're going to average those, divide that by 2, and that gives us 6.01. So g is equal to 6.01. Now, we could stop there, because that's pretty close. But just to show you this in action, I'm going to do it one more time, just to show you how this algorithm works. So let's say we'll do 6.01 times 6.01, 36.12, alright? Let's say we're not going to accept that, we want closer. So we're going to run this through the algorithm again. So let's do x divided by g. So 36 divided by g is 6.01 is going to give us this number, 5.9901. Add that to g, so add that to 6.01. It's going to give us 12, and then divide that by 2 is going to give us this number, 6.000000831. Now, that's pretty close. I would say that we can stop there, and we can say that g is equal to 6.00, which it is. So what we've done there is we've used this algorithm to calculate the square root of a number. Okay, we did not know the number at the beginning, although we did know the answer, because it's a silly example. But imagine if we were working with a very large number. This would be a good way that we could calculate the square root of that number. So that's just an example of an algorithm. Now, this here is imperative knowledge, okay? This is a how-to method, but remember that we needed to first of all provide the G. We needed to provide that declarative knowledge first of all for this to work. So that is the first part of this computer programming course. I'm just going to jump over to the terminal here and run some other examples just to refresh your memory. So let's say we want to send something to the computer, we want to store something, we can do name equals, let's say we're going to store literal value. Name equals John. Okay. So now if I do print, okay, name, it's going to return me John. Now let's say, okay, I want to send something else, store another value in the computer. I could say, okay, other name equals, running out of ideas here, let's just call him John 2. Okay, send that over. We can then say to the computer, please give me the value that's stored in the other name variable, and it will return John 2. Now let's say we were to do something like name, okay, plus other name. The computer's going to say John 2. Alright, and that's actually called concatenation, okay, joining stuff together. Now, we could even say to the computer, oh, actually, let's do name plus other name plus something else. And it'll keep doing this for us, okay? So really all it's doing is it's storing results, okay? Other name in the memory, and it's doing calculations. That's all the computer's doing. It can't do anything else other than that. So I'm just going to stop this recording now and see if anyone's got any questions, and then there's a short quiz. So that's the first topic in computer programming, and those are the things that we need to know.